Today, we are very fortunate to have Dr. Saurabh Vishwakarma with us. He is business analyst at ZD Power Group, Vancouver, Canada, and he has a versatile experience as a business analyst. Um, he is working in the field of machine learning, and more things you will explore in his talk. So, over to you, sir. Thank you.
Good morning, everyone. Good morning, Dr. Phole. Good morning, College of Engineering, Pune, and all our viewers across India and North America. First of all, a small correction. I'm not a doctor yet. I do have a bachelor's of engineering in computer engineering, but not a PhD yet. That's a path for the future. Okay, so my name is Saurabh Vishwakarma, and I will be presenting on the topic of machine learning today. Okay, first a little about myself. I currently work for a data aggregation, data integration, and data analytics solution company in Vancouver, Canada. And I have more than 3 years of professional experience in this role, developing data solutions and supporting data platforms. I've been fortunate to work with a wide variety of topics and fields within the overall data solutions sector. So I've been fortunate to work with integration between multiple data collection, data processing platforms, as well as data analytics. Some of this included analytics using techniques which we now refer to as machine learning. Some of these we would just refer to as classical statistics, as well as software development to join everything together. Okay, so what is machine learning? Machine learning refers to the creation and evaluation of algorithms which facilitate pattern recognition, classification, prediction, which are based on models derived from existing data. Essentially, we are trying to generate information, meaningful information, from raw data. Now, data refers to anything that we can record and measure. Data can be raw numbers, perhaps like stock prices that we've been measuring for and collecting, recording for the past few days, or it can be perhaps even something as diverse as the sounds of that someone speaks on their cell phone, pictures that someone posts on social media, text written on a newspaper, or anything else that we want to investigate and that we're able to collect and record. So data can be a lot of things. Essentially anything you can put in a computer, we can consider as data. Meaningful information is whatever we can extract as meaning from the data that has some use for us. It's our choice what we define as useful to us. And once we have a goal, a target of what information we want to extract, we can then design an algorithm to extract this information from our data. Now, there is no one singular technique which applies to machine learning. It would be good to if we did have a very precise meaning to machine learning. However, machine learning is used by a lot of people to describe a lot of different techniques, and this collection of techniques, well, algorithms, is constantly expanding. And also the ways that we derive these algorithms, that also falls under machine learning. That also keeps evolving. It's a rapidly evolving field, so there are always new algorithms, new techniques being discovered. Most recently, the field of deep learning is what is associated the most with machine learning. It's usually, the word deep usually refers to the fact that there are multiple layers of computation that are involved. So that makes it deep because it's not just one layer of algorithm, one layer of computation, essentially one algorithm, but rather a series. And this whole pile of algorithms and processing techniques is called a deep layer. There are actually multiple ways that you can perform deep learning. We'll actually talk about some of them in this presentation. So yeah, so usually when people talk about machine learning, a lot of people think of deep learning, but for a lot of people, it refers to a lot of techniques which perhaps we would think of as being classical statistics, but nevertheless, they do fall under the overall umbrella of machine learning. But before we actually talk more about what machine learning is, let's look at a few examples and see where it can be useful. Okay, first example. Suppose you work at the post office and you receive a vast amount of mail every day, and you want to sort all of this mail so that you can send it to the right destination. Now, you could do this the old-fashioned, the traditional way. You get a person and you get them to read all the addresses on each letter and try and identify which delivery box and which truck you want to put the mail in, where you want to send it to. However, it's a lot of work, and it would be ideal if a computer could do a lot of it. It's very repetitive. There is scope for human error, so it's better to make a computer do it. So this is actually a very successful application of machine learning. Computers have been taught how to read human handwriting. Most people don't print the address on envelopes. Instead, they'll write it by hand. So computers were taught to read handwriting, and they were able to and we were then able to use computers to categorize mail according to destination or delivery route. So this has been a very perhaps not the most glamorous use of machine learning, but it has been very successful. Another application of machine learning, this I think most of us would have guessed it already, bank checks. Nowadays, we have the facility that if we want to deposit a check at the bank, we don't always have to go to the branch to deposit it. Instead, many banks now offer mobile apps where you take a picture of the check and then the bank processes the check without you actually having to go to the bank, line up, wait in the queue, get a teller to stamp your check, and then process it in a few days. Instead, you just take a picture and the bank will do all the processing behind the scenes. What's actually happening is the bank is using machine learning models to read handwriting to understand both the recipient and the amount to be transferred. So this is again an example of handwriting recognition, same as the previous example. Again, this is something that's previously done by humans, but has now been done very successfully by machines. Another example, we all post images to social media, and usually the social media website will actually determine for us, it'll start identifying who those people are on those pictures and ask them if we want to tag them. Now, this is actually a harder problem than you would imagine. The website, the social media service, well, Facebook, might have pictures of that person wearing different clothes. The picture might have been taken in different lighting conditions, so there might be from a different angle. So it's a big achievement, but nevertheless, it's very true that we now have machines that can look at pictures and then recognize who the picture is of and then ask us if we want to tag them. So this is a case of machine learning. It's quite a difficult example of machine learning, but nevertheless, it has proven to be very effective. Another example of machine learning, voice recognition. We now have available in the marketplace a very wide range of appliances which are all capable of recognizing human speech and turning it into text, which usually you can then have it just transcribed, which is quite straightforward, or the more interesting applications where you then use it as commands and instruct your device to perform actions for you. For example, you can give audio commands to your smart speaker and tell it, okay, turn off my lights. And you now have a machine which is first understanding your voice, then translate into a command, and then implementing a command. So you have machines performing a task which was previously done by a human. Normally, you'd ask someone to turn off the lights or turn on the TV, turn off the TV. But now we have computers which are able to perform this task for us. So again, this is an example where computers are trained to recognize people's voices, and then once they've been trained, they're then able to perform the task of voice recognition and then use it by connecting it to other applications and then getting those applications to perform tasks. So normally, instead of having perhaps a person click buttons on the screen to perform a task, instead you have a computer collecting voice, and then that voice is used to virtually click on the screen. Well, you won't see it click on the screen, but it'll perform the actions for you. The common theme here is that there's a huge amount of work involved in understanding all of these situations. There's a lot of ways in which people's handwriting can differ. Same here. Here, there's not just you might not just have cases where people's faces are similar, but they're different people, but also perhaps the pictures have been taken in different ways. So it might be the same person, but the pictures were not taken. Perhaps you had pictures taken by different cameras at different resolutions, cameras with different lighting sensitivities, or cameras taking pictures at different angles, taking pictures of people smiling, people frowning, eyes open, eyes closed. So you have a lot of scenarios to cover. Similarly, you have perhaps someone is talking to their device from a far distance, from a close distance. The pitch of the voice might vary. You might have a sore throat, so your voice comes out differently day to day. Or perhaps there's just more noise in the background. So there's a lot of different scenarios to cover. And now it's theoretically possible, but not really that practical in reality to write an algorithm by hand to consider all of these scenarios. There are just too many cases. There are too many scenarios to take care of. And even if you were to try and turn all of this data, all of these scenarios into specific actions and specific situations, and then actions, there are too many to take. Instead of trying to even look at it manually, it would be much better if we just train computers to do this for us, to automate the process scenarios of recognizing them, understanding the each specific, what is the person to say, person, what are they trying to write. So instead of training a never-ending army of specialists to perform these tasks and implement them, it's much better if we can just train a computer to do it. And then once you train one computer to do it, you can just replicate it across many computers. So it does scale a lot better. So this is the main reason why, well, one of the main reasons why we need machine learning. It does scale a lot better, and for some tasks, training people is not practical because you would need to train too many people. At the same time, writing a straightforward algorithm is also not feasible because there are too many scenarios to consider. So these are situations which are ripe for the application of machine learning to make our lives simpler. Now, before we began using machine learning to solve all these problems, we did have other approaches to solve them. Primarily, we had this concept of expert systems, where you would have essentially the idea was you would find an expert at a given task. You would study how the expert does their tasks. You would create algorithms, procedures on how does the expert think, and then you would write them down, program them in a computer, and then a non-expert would be able to give inputs, send questions over to these to this expert system, and then in return, the expert system is expected to act in a similar way to how the human expert would do, and then give you some answer back. So essentially, you're creating a set of rules. So you're turning all the knowledge of the expert into a set of rules, programming these rules into a computer, and then using the computer as a standby, as a replacement for the expert. Now, this doesn't work in real life. The main problem is, okay, do this, sometimes something else will happen. So in that case, don't do this, but do that instead. So you start having a very large, almost a never-ending list of cases. So it becomes very hard to encode all the knowledge that the expert has into these systems. So your system is never perfect. So essentially, you'll spend an infinite amount of effort, but your system is never quite right. Usually, there's some over, and usually, be careful that when you make some changes to your system, you're not breaking earlier scenarios that you were handling correctly, but are not handling correctly. So we have tried to use expert systems where instead of the machine doing the learning, a human would do the learning and then tell the machine, okay, this is what you do, and then it runs very fast because the machine doesn't have to think very much on its own. It has all the rules there. The machine just has to follow the rules and then apply it. Common examples of expert systems: automotive repair. Typically, a car mechanic will enter a series of parameters into a handheld computer, and the computer will suggest scenarios and possible fixes. A doctor of conditions, and the computer will tell them a list of possible symptoms and possible ailments that this might cause. Problem is, it's not perfect, and specifically in the case of medicine, the accuracy rate often varies quite a lot, meaning the doctor cannot trust the system, so the system becomes meaningless because the doctor will work anyway each time. Why? So why you have an expert system when you need a real expert to substitute for it in every single case? Learn and adjust with the data. As the data changes, the machine can patterns that it has derived, and as data changes, the machine derives new patterns so that as new data comes in, the machine will become adaptable and will generate new algorithms for you to solve the problem. Now, so essentially, how does machine learning differ from the expert systems approach? And in the expert systems approach, the human is creating the algorithm and then the computer is just running the algorithm. In machine learning, what happens is the human creates algorithms, the computer runs those, but these algorithms then create other algorithms, and the algorithms which were created are the ones which are going to be used to process the data. So with machine learning, you are telling the computer how to read the data and to derive answers. You're not explicitly telling the computer what to do. Instead, the computer is expected to understand, conceptually at least, to look at the data and then derive the steps to solve the problem on its own. So essentially, you're giving the questions, but the computer is expected to create the steps so you can reach the answer. The reason why machine learning has become quite attractive in recent times is the flood of data that's being generated these days has become so large. The volume of data that every day is so high. It is just not possible to, well, in most cases, it feasible have much more practical to have machines which can keep up with this increasing pace of data. There are a lot of machine learning algorithms. We'll look at them. We'll look at some of them today. Many of these are conceptually simple. Some of them not so simple. For example, the most straightforward algorithm, which is still considered machine learning, is the case of straightforward linear regression. Let's say we have a series of, now you can get a human to do it. There are ways to get line to minimize your error and draw which minimizes error, and you can use a computer to perform the same. There are algorithms used to get the computer to iterate through these to the options of the lines of best fit and find the one which minimizes error. But nevertheless, this is a case of a very simple case where you can get a computer to find the line of best fit for you. So a very simple case of machine learning. This strategy is actually used by quite a few machine learning algorithms. It's not always it's not always a linear regression. It might be quadratic regression or higher orders. But this is actually quite a common application of machine learning. We think it's not the most glamorous one, but it is actually used quite often. And yes, it is machine learning. In contrast, now, deep learning. This is the more computationally intense approach, but also the more potentially rewarding approach. This strategy is now deep learning involves slowly learning from examples. Deep learning essentially is you tell the computer, okay, these are the questions, and then the computer will, and you might or you might not provide the computer the answers. And then the computer will look at the questions and then try to generate an answer of its own. And then at the end, a human expert is still required at this stage. This is a training stage. A human expert will look at what the answers that the computer has produced and compare it with what is the correct answer and if it's an incorrect answer. And then at this stage, the machine will find out did it guess correctly or did it guess incorrectly. And the process from which the machine takes the input and then reaches the output is the algorithm that's being generated by your machine learning process. And so you will show your computer a series of questions, and then after the computer generates a series of answers, it's time to check the correctness of these. And if the computer guesses correctly, it will retain its algorithm. If the computer guesses incorrectly, it will keep adjusting its algorithm. Now, this is not the way that humans learn. For example, if you were teaching a child, you wouldn't just give a child a series of facts and then ask the child the same fact again. And if the child gets the fact correct, you give the child a pass, and then if it guesses the answer incorrect, you tell them to try again. The way that machines learn is not the way that we would expect animals to learn. For example, the if you were to teach a child how to recognize pictures, if you were to then rotate the picture, you would expect the human or the animal to recognize that it's the same picture, it's just been rotated. In the case of a machine, unless you were to explicitly include another step in the training of the machine, where you were to show the rotated images and then show the straightened images and then tell the computer this is rotation, unless you actually perform this step, the computer will not be able to differentiate between a horizontal image and a rotated image. Machine learning is more like if you were to tell a person that these are the questions to the test and these are the answers to the test, and then after the computer has identified a way to start from the question and reach to the answer, and then you were to show the same questions again to the computer and then ask if the computer got the answers. Now, that's not the end of it, of course. Yes, it is useful if a computer can look at the questions and then arrive at the correct answer. However, what we're more interested in is, what if I give the computer different questions? Would it still be the correct answer? So generalizing, would our machine handle, how good is our machine at handling generalized inputs? Now this actually you can download datasets for machine learning where you teach your computer how to recognize handwriting. In that case, you will give perhaps 10 million labeled pictures of human written characters. So different people write 4 in a different way, different people write 7 in a different way, and different letters of the alphabet. And then you tell the machine that, okay, this is a 4, this is a 7, this is a 6. And then after you have shown the machine a sufficient number of images, this is the training stage, by the way. The machine has, at this stage, developed an algorithm to take an input and arrive at an output. Now, this algorithm might be correct, or it might not be, or it might actually be. This might be correct, or it might not be correct, or perhaps it's just correct for a limited set of. It's not very general. It's not very generalized. And after we have trained our machine, we will show it new pictures, not the pictures we've already shown it, but new pictures, and then see how successful is our algorithm at recognizing these new pictures and perhaps identifying, is this the same letter? Is this, if you show it if you show your machine a picture of the letter A but in a different way, and if it can recognize the letter A, perfect. Your machine learning algorithm has proven that it can handle a different set of inputs. If it cannot, if it looks at that A and says that's a C, then you have more work to do. You have to train your machine learning algorithm again with new inputs. Note, I haven't specifically named algorithms yet. This is because there are actually many different ways of performing deep learning, specifically in the case of neural networks. So you have the flexibility of telling the machine how you want the neural network to be built. Now, a neural network consists of neurons, but these are not neurons in the sense that of the human brain. The human brain contains millions of neurons, and they're very complex. The neurons that we use in machine learning are much more simple. A machine learning neuron is a small calculator. It takes in a series of inputs and it gives out an output. The machine learning stage happens at two steps where the machine learning happens. The first is each of your neurons is going to assign a different weight to the input. This is a key part of the learning. This part, we do not assign weights ourselves to the inputs. So let's say I have a neuron and it has 4 inputs coming in. The machine is going to assign weights to these neurons. And then based on the weights, an output will be generated. Now, there are different calculation functions that you can put inside your neuron. You can have a simple adder. You can have some sort of subtractor. You can use functions from calculus. You can use differentiation, integration. so on and so forth. You can make a neuron do anything. It's that's up to you what you want in the neuron. Now that's one step of machine learning, the assigning of weights to your neuron. The other step where machine learning happens is how many stages of these, how many layers of these neurons do you have? For example, the image on the left, you have one layer of well, you have 3 layers of neurons, but the input layer is not considered. That's usually provided. So instead, you have one layer which does the processing, and then your output layer, which is also considered part of the neural network. So this is essentially 2 layers in your neural net. And here you have 4 layers in your neural net, and then you can have more. It really depends on how much computational power you can have. In 3 or 4 decades back, we had relatively very simple and less powerful computers, which weren't as complex. So you could not have as many layers of neurons. So now with the advent of GPUs, you can have dozens of layers, thousands of layers, depending on how much compute power you want to put into it. The machine learning step here is how many layers of neurons do you have here, and at this point, your neural network is a black box. Yes, you know what your inputs are, and you will get outputs. The outputs may be correct or incorrect, but the connections between these neurons is going to be decided by the computer. So you have one aspect of one aspect of a machine learning process is assigning different weights to the input, and the other part is how are you going to connect the outputs from each layer, from the neurons in each layer to the next layer. So this we let the machine decide. Now you might be thinking that's a lot of options, and is that how human really thinks? Not really. This is a very simple. This is a big simplification of how the human brain works. The human brain also creates connections between neurons, and these are used to store memories as well as store actions, decisions. We are simply encoding all of this information in our neural network. It's not very precise. However, surprisingly enough, it has proven to be effective enough that it's worth doing. I'm seeing this message saying no audio. Can most of you hear me, or can nobody hear me at this point?
No, we are
Yes,
getting
we
your
can hear
voice. We are getting your voice.
So
Okay.
you are audible. We can hear
Okay.
you.
Perfect. So essentially, the reason why machine learning takes so much computational power is because we do not tell the machine, okay, these are the connections to make, these are the weights to assign. Instead, your machine is going to try assigning all combinations of weights. It's going to try making all combinations of connections. Now you can try and speed up this process of constructing your neural net or your machine learning model by setting guidelines. Okay, try these suggestions as try these weights, try these combinations, or you can let the machine try them all. Now, of course, the more combinations you try, the more likely you are to have your machine arrive at the correct answer, or at least an algorithm which, given your set of inputs that you have trained your machine with, gives the answer that you would expect it to. And then you would see that my mathematical model is giving me the expected answers, at which point you would then try it against a new set of inputs which you haven't previously shown your neural network, and then see if it still gives the correct answers. Now, if it does, then congratulations, you have a working machine, a machine taught model. Now, machines don't really learn. Well, at least not in the way that humans would learn. So you can provide inputs that vary slightly from the ones you trained your machine with, and you should have a reasonable expectation that my that the model should arrive at a reasonable answer. However, if the input changes a lot, if the input diverges, then it will most likely not return to you the correct answer. So that's why even when we do use machine learning, we have to be cautious that there are limitations to what your model is expected to know and what it is not expected to know. Now, you might be tempted to think, okay, I will give my machine learning model a combination of all possible inputs that we know of, and it should give me correct answers which are correct in all cases. Yes and no. Now, of course, the more inputs you give, the more answers you will receive, which are correct. However, you run into the problem of overfitting. The best way to think of overfitting, the best analogy for overfitting would be, let's say you had a student and they were to read the questions of the exam before the exam started. Yes, for those questions, they would know the answers, and if they were to write the exam, they would get all the questions correct. They would be very successful in terms of passing the exam. But do they know all the subject material? Maybe, maybe not. This is the risk that you run with excessively training your machine learning model. It knows the answers for those specific questions, but it might not know answers for questions it has not seen before. So in that case, we could either try training the machine learning model again, or perhaps we could try being more focused in our training by perhaps performing steps to clean the data before providing it to the machine, or other tasks to simplify the data, or give more provide the model with additional means of deciphering the data. So it would, at that point, it would no longer be a purely machine trained model, but it would be a more effective, the useful model. Okay. The process where we provide inputs to our machine is called labeling. So you have a series of facts that you're going to provide to the input, or you have a series of inputs that you're going to provide to your machine, and you will tell your machine ahead of time that, okay, this is my question, and this is the correct answer. In this case, you've provided a label to the machine, okay, and you will let the machine process that input and then try and arrive at the correct answer. And after giving it a large number of inputs, we can then have an expectation that the machine will learn. So essentially, we're providing a large number of facts to the machine. We collect as many facts as we can, and then, but not too much. And then each piece of observed data might vary in a different way. We call those features. So let's say you're providing pictures, you're providing satellite images of weather maps. So providing pictures of the Earth. Now, those pictures might contain different shapes of clouds. It might contain different colors, which represent different weather phenomena. These are your features. You can think of features essentially as variables. You can also think of them as dimensions. In a sense that they are independent of they might be, well, we expect them to be independent of each other, but they do all exist they will vary across each of your input, and after passing them through your model, you would then expect to have provided a series of different scenarios. Each scenario has something different about it. Well, it could have many things which are different about it. The features would be very different about it. And you would use these labels to tell your machine that, okay, this is what is different about it. And then you will let the machine run a few passes through it and then find a way to take your labels and then give you the right answer. essentially you want the machine to give you a prediction. So for example, in the case of weather prediction, you might give a series of pictures that indicate a storm is imminent, pictures where a drought is imminent, pictures where a flood is imminent. Keep in mind, we're not actually teaching the machine how weather works. We're not teaching the machine that, okay, if you see these clouds coming, then a storm is forming, or if you see these clouds dispersing, then there's an area of low pressure or high pressure. You're not teaching your machine the laws of physics. Instead, you're just giving it inputs. There might be pictures or observations of the weather. Perhaps a weather forecaster has looked at these and assigned labels to these. So you might be giving pictures and saying that, okay, this is storm. This is a storm. This is a hurricane. This is a tornado. This is a flood. This is a drought. This is a flood. Oh, this is a flash flood. This is normal weather. This is sunny weather. This is cloudy weather. And after you show a large number of these images, the expectation is that the machine has now created a mathematical model of its own, so that if you were to provide new images, the machine would then give you a prediction of the weather. In fact, this has actually been implemented in real life. And Google, and there are a few other weather companies that have specifically created machine learning models where they don't use specific where they don't use complex physics models of the weather. Instead, they just look at weather images, they look at weather maps, and then they tell you what is the weather going to be like right now, and they'll take a guess at what the weather will be like in the next 5 minutes, the next 10 minutes. This is actually very useful because it can give you a reasonable prediction of what is the weather going to be like where I'm standing now. Normally, if you were to watch TV and receive the weather forecast would be given for a specific location, perhaps where the weather station is located, or perhaps where the broadcast studio is located. And if depending on how far your house is from there, or perhaps your city is not mentioned in the forecast list, that might not be the weather that you're experiencing, simply because there are too many locations to cover. But now that if you have a computer looking at all these weather images and then telling you that, okay, this is what the weather is going to be like at a given location, you're now able to tell people, okay, this is what the weather is going to be like at your house. And if you were to go at this location, if you were to plan a trip down the road, down the forest, down the hill, and but which day you're planning it, this is what you should expect the weather to be like. Is this practical for if we were to use human weather forecasters and have it implemented for every single person on Earth who wanted to travel somewhere? No. Is it now possible to use a machine to make these predictions for you, make these predictions for each person? Yes. There's an interesting way in which machines it's not necessary to always teach the machine what the correct answers are. You can just give it you can give it a series of questions and let the machine think of its own. And you can also let the machine deduce the rules of the scenario on its own. When you give the machine the questions and the answers, we call that supervised learning. There are two main categories of supervised learning. One is classification and the other is regression. In both cases, you give pre-assigned labels to your input. So let's say you have you have a collection of photos of people, fruits, vegetables, anything. You can then look at these, that you then have a person attach a label to each photo. So you might have a photo which says pear, you might have a photo which says apple, you might have a photo which says Bob, John, Apple, Linda, and then you would then provide these photos to your machine and let the machine identify, okay, these are pictures of Bob. If I was to now look at another picture of Bob, what would it be? Or alternatively, you could provide a machine a series of pictures of cancer images of cancer tumor images, well, you could provide it pictures of cancer tumors and then label them as this is a cancer tumor, or you could provide, and you can also provide pictures of regular uh, regular tissue without non-cancerous tissue, and then tell the machine that, okay, give it a label that, okay, this is non-cancerous tissue, and then after providing these known facts to your machine, you can then let the machine identify these identify the patterns of how to reach from the input to the output, which is the known answer. So that's supervised learning. Essentially, the supervision comes from our labels. So the classification is concerned with looking at a given collection of categories to find the one that best describes your input. So in case if you were to provide it a series of pictures of a person, then your machine will look at each picture and then decide which picture in my known list of facts does this match most to. So if you were to provide a machine with only a picture of a cat and a dog, and you should expect your machine to become very effective at distinguishing between pictures of cats and pictures of dogs. However, if you were to then provide a picture of a tiger to your machine might decide that's a dog. It might decide it's a cat because it hasn't seen it before. Regression is concerned with taking a series of measurements and then predicting some other value. The most simplest, of course, is linear regression, where you, for example, if you were to give it a series of prices of a given stock for a series of months, and then you ask your machine, okay, what is the price likely to be? What is the stock price likely to be for the next month? Then your machine would find a trend and then make a prediction. Now, regression is perhaps not what most people would think of when they think of machine learning. It's actually a well-known statistical technique. However, it's possible to implement it in a variety of ways, and the regression formulas that we derive at the end can be either derived using classical statistical approaches, or we can use more exotic methods where the machine will try and construct different lines of best fit on its own, and then try and find the line which has the least error. There's different ways that you could do this. You could create your own algorithm. You could define your own criteria for what counts as error and how you want to minimize it. Perhaps you're looking for the least squared error. Perhaps you're looking for the least cubed error. It really depends. So now, regression is one case where the dangers of overfitting come to mind. Let's say I give my machine all of these inputs. If I was to try and get a line of best fit, which was to pass through all of these inputs, I would likely have a line which is not really a line, but more of a curve, probably a polynomial of a very high degree. Would it pass through all my inputs? Yes. Would it provide exact answers for my known inputs? Yes. Is it expected to work well in real life? Probably not. So with regression, it's very important to not overfit, but instead keep a level of coarseness to our final answer so that it works in more general cases as well. So these are cases of supervised learning, where you provide your machine your questions and the answers, and then you let your machine find the best route to take a question and then arrive at the answer. Sometimes your input does not come with labels. So you might give a series of facts to your machine, but you might not tell your machine what it means. Instead, you will let your machine try and understand what the question is and what the answer is. So that's essentially, we're not supervising learning process by giving it labels. For example, the image on the right, we would tell the machine that, okay, everything on the top right corner is output 1, and everything on the bottom right corner, on the bottom left corner is output 2, and then you would let the machine figure out what's the line of best fit. On the other hand, with unsupervised learning, you would provide the exact same inputs to your machine, but you would let your machine try and figure out the patterns in the data, and the answers could be unexpected, but also quite interesting. The unsupervised learning has proven to be quite good at building classifiers where your machine is able to look at inputs and then identify common trends of its own. For example, let's say one case where unsupervised learning comes to mind is, let's say you are you're a geologist and you're digging for rocks and you find different types of rocks. Uh, let's say you don't have access to you don't have access to a lab, so you cannot identify the chemical composition of these rocks. Nevertheless, you are able to visually look at these rocks and see patterns. Maybe some rocks have crystals, some rocks have large crystals, some rocks don't have crystals, some rocks are made of layers, and you would provide your machine with pictures of all of these rocks, and you would let your machine do the classification. Okay, these are the rocks that have layers, and perhaps, and then these are the rocks which are crystals. These are the rocks that are mixture. These are the rocks that seem to have formed from molten ore. And although the machine might not know what these exact groups mean, at a later stage, an expert might be able to look at these images and say, okay, these are sedimentary rocks, these are igneous rocks. So essentially, you would let the machine do the hard work of trying to find the underlying trend within the data. This is very useful if there's a large number of data sets to be, if your data set is very large. For example, let's say you have 10,000 rocks and you have only one person. Is it realistic to expect one person to look at all the rocks and classify them? Not really. It'd take a very long time. But is it possible to have a computer do it? Yes. Once you train your machine with a few hundred rocks, at that stage, all you've done is you provide pictures of the rocks and then let your computer let the machine decide. Okay, these are how to classify them. You could then you can then have your machine learning model run on many computers, pass all the images of rocks, and generate a series of predictions. Some of these predictions might not be meaningful classifiers. Some of them might be, and so essentially you have outsourced a lot of the manual grunt work to a machine. So this is an example of unsupervised learning where you let the machine make deductions on what the data means. Another very effective application of machine learning is noise reduction. Let's say you've taken pictures and the picture was taken with a blurry camera, or it was very highly compressed, and the end result is not a very clear picture. For example, let's say you have a picture of a koala. Would a person be able to distinguish that it's a koala? With great difficulty, but possibly they might be. Now, this is our final picture. How would we arrive from our noisy input to our refined output? We would train our machine, and we would give it pictures of give our machine pictures of noisy input and pictures of the fixed input, but not necessarily tell our machine that these are fixed inputs. Instead, the machine would derive the relation between these. And once it has derived this relation, you can then start passing in other pictures. Now, noise reduction sometimes works very well, sometimes not so well. A more special use case of noise reduction is simply improving the resolution of an image, in which case you provide multiple images in different resolutions. So if you were to provide a low resolution image and then a medium resolution image, and you were to pass them through and allow the machine to construct a model which maps the low resolution image to the high resolution image. At that point, if you were to then pass a medium resolution image, your machine would draw the image for you and produce a high resolution image. This is actually done now for computational photography, where where the the final image that is produced is much more accurate than what the camera sensor on its own would have been capable of generating. What's essentially happening is your sensor is taking a noisy image, perhaps not as bad as this, but quite bad. And after having trained your machine to map noisy images to sharper, crispier images, your machine would then give you sharp, crystal clear images. What's really happening is your machine is drawing in the details for you. And you have to be very careful with this. You have to make sure that when your machine is drawing in the details, it doesn't miss too many out. Otherwise, the image doesn't look realistic. At the same time, you don't want the machine to draw too many details where the image looks unrealistic, as if it was generated by animation software, not actually a real picture. This doesn't apply just to pictures. This also applies to noise, where let's say a microphone has taken a recording of a person's voice, and the microphone has not been able to capture a perfect sound input. Let's say there's noise in the background, or perhaps the microphone is not of a very high quality, so the sound signal has not been captured very well. So you have a noisy input. Now, it would be possible to, it has been in the past where we use signal processing algorithms, known signal processing algorithms, to try and refine the sound and fix it. Now these algorithms are fixed, so it is expected that under certain conditions, they will refine the sound very well. Under certain conditions, they will not refine the sound as well, and they might actually make it worse. So this is a case where machine learning can be used to improve the quality of the sound without explicitly having to create new signal processing algorithms. You would essentially provide the machine two separate audio samples. One is an audio sample which has deliberately had noise added to it, and another audio sample which is clean, and you would allow your machine to create the relationship between them and identify that, okay, this is my noisy sound input, and I will arrive at a cleaner sound output, and then you can then use this to filter and improve other sounds. This is now starting to be used now for everyday mainstream equipment. So it does take a lot of computational power to run this machine learning model, and first to train it, and then also to just run the model when it's processing new inputs and to generate your predictions. However, it is expected to become more common in the coming years, where the sound that our audio recording applications are outputting is much clearer than the sound which is actually being received in. Perhaps one day you might even see this on WebEx, where if my noise is not, if my voice is not coming in very clearly to you, WebEx in the future might decide to filter and smooth out my voice, make it sound more clear, make it sound more realistic. So essentially, you're using machine learning to perform the denoising process. You're removing anomalous inputs or filling in the blanks. Now you might think that, is this not similar to regression in a way, where you're trying to smooth out samples? Yes, it is. It really depends on how you use your algorithms. This is very similar to typical computer science, where you might have algorithms to perform searches. You might have a simple breadth first search algorithm, but depending on what your specific problem is, you can write your problem as convert it into a mathematical graph, and then adapt the original algorithm to solve your problem for you. In a similar way, you can use a generic algorithm and then have it applied in different ways and use it to generate the intended result, which is what you're looking for. Another case where machine learning is used Specifically, where unsupervised learning is used is sometimes our samples have more information than we need. For example, let's say you're taking weather samples and you're taking and you're recording information of weather in a desert. Now, in a desert, the rainfall is always going to be zero, or almost always zero. So in this case, you don't even need to provide a machine learn. You don't need to provide to your machine the precipitation level as an input, just because this is a dimension that's going to stay constant almost all the time. So let's say what would happen if you were to provide your precipitation as an input. Your machine would look at the precipitation inputs and all your other inputs, all your other dimensions, such as wind speed, wind direction, temperature, cloud cover, uh, length of sunshine hours, length of nightfall hours, and it will look at all of these dimensions and then try and arrive at the final prediction, which might be what is the temperature going to be at various stages of the day. So your machine, so the more dimensions your machine model has, the more time it will take for your machine to construct the model in the first place. So by removing dimensions, you are going to make your machine model run faster without losing very much detail. Yes, your precipitation level will no longer play a role in how you in how your machine model determines temperature for the day, but that might be acceptable for us if we already know that it only rains one day in a year in that desert. So most cases, there is no need to even consider the precipitation. The benefit will be that your machine learning model is created much faster, and it might be just as almost as accurate, and it's ready to use much quicker. Another form of machine learning is reinforcement learning. Let's say you are you're told to play a game, and you're told what the rules of the game are, and you are given a metric of how to succeed in the game. Maybe the metric is to win in the fewest number of moves, or the metric is to have the highest score. But I don't actually tell you what's the winning strategy. How am I going to play the best? How am I going to play at my best and win and maximize my reward? Perhaps get the highest score or finish the game the shortest number of moves. So in real examples, how if I was to let my computer learn how to play chess, or even how to play more complex computer games where where the final score is known, and in this case, my machine will try and play the game, and each time it plays the game, each time it tries a given strategy, it will receive an end result at the end of that after making a certain number of moves, and it will recognize that, okay, for this strategy, this was the final reward. Is it possible to get a higher reward? In this case, it will make some changes to the previous strategy and then try again. If the reward is now higher at the end, maybe it tried a new strategy in playing chess and it managed to win the game in a fewer number of moves, then that strategy is better. And after playing a certain number of a huge number of games, your machine will now have derived on its own a winning strategy, or more like a collection of strategies depending on how the game changes. So essentially, you are letting your machine act as the agent, and your machine is going to make a series of actions within an environment. The environment might be a chessboard, and now the environment doesn't include just the chessboard, but it also includes the opposing player. So your machine is one of the players in your chess game. It makes a move. The environment, which is the chessboard, and the opposing player makes a move, and so the environment is changed. So now your machine has to react to this changed environment. Now your machine could your machine has a series of different possibilities to choose from for how to react, and as it's a machine, it will probably try them all, and eventually it will find a specific action which works best, or a series of specific actions that seem to work best for the time being. And as the game continues, as the environment keeps changing, your machine will end up with a series of with a collection of strategies for a collection of different environments. Now, this is not how a human would typically play chess. You would not expect a human to memorize 500 million strategies of how to play a game of chess depending on the board layout, but this is how a machine play chess. And it turns out machines can actually beat humans with quite a regularity now with this approach. So this is essentially reinforcement learning, where your machine is the agent and it's making decisions, and the environment is reacting to those changes, and then the machine finds out how the environment has changed, and then the machine takes new actions, and then finds out how the environment changes again. And we are now able to, after letting the machine train itself with a number of environments, the machine becomes quite effective. No, there is no correct result. I'm not necessarily telling the machine that, okay, this is a series of moves that you must make to win this game of chess in the best way. We are not providing any additional context to the reward uh, and what the environment is. The machine is interpreting the environment and interpreting the reward and making the relation that, okay, it made an action, and based on that, it has the environment has changed to a certain state, and its reward has gone up or down. And based on that, the machine can decide, okay, was this a good action or was this a bad action? And it might decide that an action might be good in the short term but bad in the long term. We are not teaching uh, all these to the machine. The machine is able to learn these on its own. Now, this will take a lot of processing, a lot of memorizing, but at the end, it is expected that the machine will have learned quite, uh, if not all winning strategies, but a large enough collection of winning strategies that is able to perform quite well within a limited series of known constraints. For example, in the case of a chessboard, the chessboard is not going to change very much. The rules of chess will remain the same. So if the machine learns a series of strategies, those strategies will hold. Now, in cases where the environment is going to change very rapidly, reinforcement learning might not be the best approach for a machine to use, simply because all the strategies that your machine has managed to learn might no longer apply after the machine is finished training itself. Another form of machine learning, currently the most vigorously researched form of machine learning, is deep learning. In deep learning, we mimic the human brain. Now, it's a very big simplification of how the human brain actually works. The human brain has a collection of cells called neurons, and as we think and as we remember actions, our our brain creates connections between neurons. In fact, as we get older, some of these connections degrade, and we're no longer able to think as effectively. Unfortunately, old age applies to humans, but it doesn't apply to machines. And similarly, now deep learning is actually a very old concept. It's been around since the 60s, or possibly even earlier in various interpretations. However, the main difference between deep learning research in the 60s and now is the level of computational power available to create a large neural network in the past was very limited. So the deep, so the neural networks were not very deep. They did not have very many layers, so they could not encode very complex decisions and complex algorithms within them. We now with mainly high-powered graphics cards, to a certain extent, also high-powered central processing unit CPUs, so processors, but mainly just very high-powered graphics cards were able to create much more complex neural nets. But the main concept is the same. A neuron in the machine learning sense refers to a small mathematical. A neuron is not really, now this is a simplification. A neuron is more like a mathematical function. So that's your function, and it has a series of inputs. It assigns weights to these inputs, and then it generates an output. The output here and here is the same. It's just that the output is being given to. It's just the neuron has discretion. Well, your machine has discretion on how it's going to send the output over to the next layer. So with deep learning, your machine is going to be given a series of inputs. This is your input layer. Although these are represented as neurons, they're not counted in the number of layers of our neural net. So you could think of this as a layer 0, and then this is the first layer, and this is the second layer. The deep learning stage is happening at two locations. First is the weights that's being assigned to here. So let's pick the simplest model of machine learning neuron, a weighted adder. So your neuron is going to take a series of numbers as your inputs, assign a weight to them, add the total number, add all the weighted inputs, and then produce an output. Could do something more complicated as perhaps perform differentiation, integration. Usually when machine learning models are created, we can specify how many layers of neurons we want and what function each layer should do. It is still a topic of active research on how to connect these on how to position these layers and what each layer should do. The machine has the freedom to decide how to weight these inputs and then how to wire up connections between each layer. So the machine can decide, okay, maybe this neuron should not connect to both inputs, but only send its output to one neuron of the next layer, or maybe this this neuron should not actually send its output at all. So it becomes essentially a large series of combinatorics options to explore. This is where the large computational cost comes in. Your machine is going to explore a large number of combinations of weighted inputs as well as connections between layers. Now, the more layers you have, the more combinations you have to check. However, the more layers you have, the more complex decision making you can encode in your machine learning model. Now, ideally, if you had a huge layer of a huge number of layers, you should be able to receive a more accurate predictions from your machine learning model. However, that it could take weeks to train your model. It would become a trade-off of how soon do you want your machine learning model to be ready versus how accurate you want it to be. So essentially, we are encoding human thinking into a quite crude form of representation for computers to process. However, it has been proven surprisingly effective, and neural networks are used everywhere from spam filtering to medical imagery detection, as well as detecting objects on maps. So, for example, you could use Google Earth and get images from it, and you pass it through your machine learning model. The machine learning model could distinguish between, okay, this is a building, this is a road, this is a car. You can use it to differentiate between faces. Essentially, your machine learning model is going to turn all of the information about a picture of a human face, so shape, different angles of the different parts of your face, different differences in skin tone across your face. So if your eyes are closed, if your eyes are open, if you're smiling, if you're not smiling, if your teeth are showing, if your teeth are not showing, all of that information is going to be encoded as various weighted inputs and connections between layers. Now, you might imagine that this approach is not going to be very flexible, and you would be correct in thinking that. However, as long as the inputs that we're passing into our machine don't change very much, we can expect the machine to provide reasonable predictions of the output. Essentially, we're able to use neural networks to explore all combinations of changes to the input. It might take a very long time for the machine to process all the different inputs and then to generate all the different outputs, but it can be done. This was something that back when we had our expert system, it was not possible to, well, not easy to implement. So while we had our expert system, it was quite difficult to encode all possible combinations of inputs and outputs and provide a reasonable prediction for each of them. However, with our machine learning model, we are now able to outsource this task to a computer, and depending on how much computational power we're willing to throw at the problem and how much time we're willing to wait for it, we can allow our machine to explore as many combinations of inputs, changes to inputs, and spend as much time creating as many complex layers of decisions with the hidden caveat that the decisions are really just mathematical functions that either produce an output or they might not produce an output. And in fact, most neurons even have an activation layer. Well, not even activation layer, but they have a bound for how high must the input be for the neuron to get triggered. This is actually very similar to how neurons in the human brain are triggered. They must receive an impulse of a specific size, otherwise the impulse is ignored. Similarly, this neuron might only decide to activate if the input crosses a certain threshold. So yes, it is a nuanced calculation, and as you build more layers, your system is able to encode quite complex logic to it. The downside of this is that the end result machine learning model is essentially a black box to us. It would be very hard to just look at a machine learning model with, let's say, 15 hidden layers and then the output layer, look at the connections between them, and then say with confidence, okay, I'm going to send it a picture of a cat and I should see a picture of a cat. In fact, if you've trained your machine with a million pictures of cats and a million pictures of dogs, while it might be very good at recognizing them, if you were to then provide a picture of a penguin, your machine would either could either give you a prediction with a certain level of confidence that, okay, this is a cat, this is a dog, or this is, I don't know, but this would only be a prediction. So it's possible that your machine could look at a picture of a penguin and say with 99% confidence that this is a cat. So even with neural networks, your machine learning model is quite specialized. This is why they're usually used this is why we usually use machine learning for things they're good at, and we mix it with regular programs, so regular logic. So usually so we would use machine learning to generate certain algorithms, and but the overall system would consist of explicitly specified algorithms. So the regular way of writing computer programs, where you take certain inputs and then you have a deterministic method of producing certain outputs and combine them with machine. For example, you might use machine learning for a classifier, or you might use machine learning to perform regression, but after that step has been performed, you can then use regular programming to perform the rest of the tasks. In fact, our smart speakers are a very good example. So they might use machine learning to recognize your voice, but once they recognize your voice, the series of actions that they are going to perform is quite well defined. So for example, your machine learning algorithm might recognize that I'm saying turn on the kitchen lights, but your smart speaker is, or at least the cloud backend to it, also will eventually take this input, your voice command, and then check with a specific, an explicitly coded algorithm, which will say, if if I have controls over the lights, then turn off the lights. If the command has been received. So if I was to say turn off the lights, but the smart speaker device doesn't know that there are any lights in my house that it can control, then it won't do it. That algorithm is not it's not derived from machine learning. However, the overall system is combining machine learning generated algorithms with algorithms written by people. So that's the main takeaway of my presentation, which is Machine learnings are a way for us to generate algorithms, and they do not make obsolete the traditional procedure of writing algorithms. For example, if you were to do pathfinding, you might find it's actually more efficient to write an explicit breadth first or depth first search algorithm rather than letting a machine spend time to create a model which will end up giving you the same, which might end up giving you the same results as those algorithms, but not always. So yes, so that is the end of my presentation. Do let me know if you have any questions, and I will try to answer them to the best of my knowledge.
I think no query. Thank you very much, Saurabh, for such informative and detailed session. Um, Machine learning is the future for wearable, so it will help all of the experts and teachers who are in the group, definitely. So thank you very much for your valuable time and such a nice session.
Thank you very much, Dr. Bole. Thank you to the audience for attending and for giving me the chance to present to you all. I see there is a question.
Yeah.
Okay. So so the classifier is okay. So you would use machine learning to generate your classifier. You could use a variety of algorithms to arrive at your classifier. However, or someone might have already. Okay. So a classifier is an algorithm that takes a series of inputs and can arrive at outputs for those specific for known ranges of inputs. So you might either use a classifier that someone has already generated by training their own machine learning model to do it, or you could generate your own classifier to do it. So I think the question is not necessarily how to select a classifier, but unless you're taking a classifier that someone has already written. But how do you want to go about creating your own classifier? You could use supervised learning. You could even use unsupervised learning for it, although it's faster to do it with supervised learning. And once you've arrived at an algorithm which takes a series of inputs and gives you a series of outputs, such that you have a classifier for recognizing people's faces. So the classifier is an algorithm which will take a look at faces and say give names to them. So at that point, the question really is, are you going to create that classifier yourself, or do you want to use a classifier which already exists? And how are you going to, and what are the steps that one would go about in creating the classifier? Did that answer your question on the chat box? Okay, different tools for using machine learning. Okay, there's a lot of tools for Python. You can use the TensorFlow library from Google. There's even a library for Java, deep learning for J. You can there's even a machine learning framework for the .NET framework. So if you're writing in C#, then you can use ML.NET. So there's essentially libraries for a variety of different frameworks, and then there's there's even formats that you can use to provide to exchange models between different libraries. I don't think very many people use it because it's very cumbersome. But yes, you could even have your system implemented with different in different languages. So you might have your machine learning. You might have the machine learning section of your system implemented in Python, but the other parts of the system implemented in something which runs faster in a computer, like Java or C#, or even C++, if you want to go really fast. And then you would have those interoperate. As far as learning, you could even use R to do it. There's a lot of libraries in R which you can use to create, which you can use to first train your machine learning model by giving them a series of values and then saying that, okay, these are my values, this is how you train it. And then after after the library has created an algorithm, you can then run that model against a new set of data, your new input, and see how successful it is. So there's a large number of libraries out there. In fact, TensorFlow is just the biggest name. There's a large number of things out there. Did I answer that question? You can respond in the chat. I will respond to the next question in the meantime. Okay. For something like human disease detection, what are the sources for giving supervised samples apart from internet images? Okay, very good question. Typically, it's done. This is done by medical facilities. So you might have a doctor giving X-ray images to a machine learning system. This was done, I believe, with some medical research institutes in the US where they had doctors researching cancer who would give images of cancer tumors to IBM Watson and then label them as, okay, this is cancer, this is not cancer, this is a benign tumor, this is a malignant tumor. And then after that, it would give you, after this was supervised learning, by the way, and then after giving a sufficient number of images, the expectation was that the machine learning system would be able to look at these images and then look at fresh images and then say that, okay, this is cancer, this is not cancer. However, I don't think it is that successful in that role simply because there are a lot of nuances in this, and in specifically cancer, which is cancer, there are a huge number of ways. There's a huge number of conditions which are classified as cancer. So it's not just really one condition as cancer. Like there's leukemia, you can have cancer. You can have cancer of the brain, you can have cancer of the lungs, you can have cancer in the stomach. So of all these different types of cancers, it's becoming difficult for the machine to provide meaningful advice. So yeah, internet images is not really the best way to train for medical for medical human disease detection. You'd usually get a medical specialist. You would usually partner with a hospital and give images. Now, so far, the utility has actually been questionable, simply because the machines are able to perform very well for the known inputs. So essentially, that's like if I was to give you an exam and give you all the questions and the answers, and I expect you to know all the answers, but as far as like giving you new questions and then asking the answers, that has not been that reliable so far. So medical applications, there's been a lot of progress, but I don't think we're still there yet. Although we'll probably reach there in the coming future. As far as using machines to develop medicines, there has been some progress on that. There was some research. There was a publication a while back where they were able to provide to the machine labeled inputs. So again, supervised learning, and tell it that okay, these are specific molecules for medicines, drug molecules, and these are the diseases that it cures. And they also provide as an input a large database of all molecules and what the active site of the molecule is. So a molecule can be very large, but maybe only part of it actually needed to actually treat a disease. And the machine learning model was able to find similar molecules which also had the same active site. So essentially found substitute medicines. Although it's not clear how replicable those findings were and if they would actually be able to work on a large scale. But yes, there has been there has been progress on this, but we're not completely there yet. Okay, another question. Does the input data affect accuracy? Accuracy is a difficult question. So the thing is, yes, it's important to be accurate. At the same time, you don't want to be too accurate. For example, for that regression problem, where if you're trying to like find a line of best fit, you don't actually want it to be too accurate. In fact, because of machine learning, we now have demand for processors which can deliberately reduce the precision of numbers when they are performing operations, because it has been found that introducing this fuzziness actually makes the machine learning model give more accurate results, or at least the predictions become more accurate. So somewhere down the line, what's happening is your machine learning model has a huge number of layers, and you're passing your input numbers so many different layers that your output numbers are having, after all those operations are done, your output number has a huge number of digits both before and after the decimal point, and perhaps that's actually confusing the machine as it's trying to generate an algorithm to actually map these and to generate predictable outputs. So instead, what they're trying to do now is actually reduce the precision of these numbers during the calculation step. So I would say that accuracy of the input, it really depends on what you're trying to provide. Like if you're trying to provide pictures, then yes, you need the picture to be sharp enough to be readable. At the same time, you don't need to give it like super high resolution images because the machine needs a certain level of generality. Similarly, if you're giving machine a series of numbers, you don't have to necessarily give it very high accuracy numbers because it's assumed that there's going to be a line of common trend. So your machine's going to have to your machine learning model will drop precision at a certain number of point. So how to gain accuracy in image analysis? For this, you would have this is actually an area of active research. With machine learning, there is no real known perfect answer. As okay, this is the perfect algorithm to recognize handwriting. It's more like we have an algorithm which is accurate for these training images that we provided, and then we tested it with a new set of images, and then it found maybe 80% of them. So it is reasonably accurate. Improving them, it's hard to say how. What would be a definitive way of improving them? Because simply because essentially when you're okay, so machine right now image recognition is being done using deep learning, and for deep learning, usually we have people specify the number of layers and what each specific layer does. You may have a layer that does differentiation, a layer which does some other form of filtering, of cleaning your data. So that part is still human configurable. So you have people experimenting with, okay, I tried this and it seemed to work. So okay, maybe that's the best way of doing it. And then someone else tries something and it tries something slightly different and it works better. So then everyone agrees, the consensus that okay, this way is slightly better. So let's try that for now. And then it's an iterative process. It's at this point there is no fixed algorithm which will give you all the correct answers. Minimum system requirement for a deep learning approach. Excellent question. If you're making a small model, you can just run it on a standard PC. You could even use your CPU to run the deep learning model. If you have a huge number of layers, at that point you would need typically a high-powered graphics card. It doesn't even have to be a high-powered processor. Just need to have a high-powered graphics card. The reason I say that is high-powered graphics cards have a large number of cores, and each core in a graphics card is able to do simple calculations. But because a graphics card might have, let's say, 1,000 cores, it's able to do 1,000 simple calculations in parallel. And when we say calculations, essentially each core is going to act similar to your neuron. So so while your processor might have, let's say, 8 cores or 4 cores, it'll simulate 4 neurons in parallel. Although your processor might be able to simulate very quickly each neuron. So let's say a processor takes a few microseconds to process 4 neurons. So but your graphics card takes a millisecond, so a lot longer. But if you have thousands of cores on your graphics card, overall, the cumulative number of neurons that your graphics card can process will actually be higher. So you need a more powerful graphics card. This minimum requirement, you're probably looking at some graphics card with at least several hundred cores. Right now, you can get graphics card with thousands of cores, although they are quite expensive. If you're just doing it for small amounts of research, you might consider just renting one on something like Amazon AWS or Microsoft Azure. There's a lot of people who've already come into this problem, so you can actually rent computational infrastructure on the cloud. You can rent like 10 graphics cards or 20. Like you probably wouldn't want to buy 20 just because a graphics card can cost a lot. Like you might cost like $1,000 for a graphics card. Do you want to buy 20 graphics cards if you're like just doing it for experimentation? I guess it depends, but it could get expensive. Whereas if you just rent 20 graphics cards for a week, it would be a lot cheaper. So yeah, there's different pros and cons of either buying your equipment or just renting it or renting high performance equipment for short amounts of time. Any more questions?
Yes, sir. For developing all this machine learning and deep learning means in research for research, means which platform to be used means what do you think? Whether the Python to be used for biomedical signal processing or whether to work on MATLAB like platforms?
I think that there's multiple parts to the answer for this question. The first part is Python and MATLAB are programming languages, so it's not really the programming language that's going to that's going to be a major consideration, but rather the libraries for that language. For example, mm, I know that Python has a huge number of libraries. I don't know if MATLAB has that many libraries, so it's not really about the programming language the platform, but rather how many libraries do you have available? Because you don't want to write all this like you don't want to like reinvent the wheel by writing all these. So if people have already written down the algorithms that can generate the machine learning model for you. Like if you were to like create machine learning models, you wouldn't actually necessarily have to implement all the algorithms from scratch. Instead, you could use something like TensorFlow, which is available for Python, Java,
Yes.
or C++, and some other languages as well. But I think they support Python the best. You could also use MATLAB or R. So I think at an introductory level, you can use anything. You could even use R, which is a very R syntax and R syntax and MATLAB syntax is very similar, but R is free and has a huge library of packages. Python has a huge number of libraries, but involves a bit more programming experience than R. And if you're trying to like productionize this, then you could run this on Java. For example, when people make apps for smartphones, they're able to now use the machine learning technologies. In fact, the iPhone and Android phones now include machine learning libraries, so you can actually create your own machine learning models on the phone. For example, for iPhones, the iPhone has a built-in system where it tries to learn from what are your phone usage patterns, and it will use that to charge your phone only to 100% when it knows that you're about to use it. Now, why does it do that? It's because when you charge your battery to 100%, if you charge it more than that, the battery capacity starts to degrade. So the phone implements a machine learning model which learns when are you using the phone the most. That's reinforcement learning because cannot supervise, but it is able to like try and predict your schedule, and then let's say you plug your phone in late at night, and the phone expecting you to wake up in the morning. So the phone will actually stop charging late at night, and then just before you're about to wake up in the morning, it'll start charging again. So that when you wake up, your phone is fully charged, but you don't actually have to unplug the phone at night to preserve your battery. So as far as platforms, there's a lot of platforms now. As far as developing it, also as far as like put like leveraging it. I hope that answered your question.
Yes, yes, you are, sir. Thank you very much.
Okay, thank you, sir. Thank you very much.
You're welcome. Yeah.
So I conclude here that this session is over.